Junho. Thanks for the nice talk. So now I guess we can move on to questions. So I know, Stephen, you have some questions in the chat. So do you want to start?
Yeah, so I put 3 questions in the chat. So the first one is just a very superficial question.
Okay.
Okay, I mean, I can read them. In all the experiments, it looked as if when you had the mixed SRI centrifugal instabilities, the SRI was always on the top.
You mean the top in terms of really the vertical location?
Yeah, near the free surface. Was that just accidental, or is that a persistent phenomena?
It's not I will say it's not a constant manner. It was not always on top. And I guess I didn't explain well why there can be 2 instabilities. It's that first of all, when we have the stratification, it is not only density who's stratified, but it is also viscosity who's also stratified in a vertical direction. So it means that in fact local Reynolds number is different vertically. So even though we consider same Brunt-Väisälä frequency, but in the end we have a different local Reynolds number.
Yeah.
And depending on local Reynolds number, there's a chance that at this like let me say small local Reynolds number, maybe SRI is more unstable than centrifugal.
Yeah. Okay, that makes sense.
Yeah. So we had the local Reynolds number variation.
Yeah.
And
okay.
in fact, that explanation is already written in the paper, but I just didn't explain during the presentation to avoid more confusion. So
question 2 was when you showed for those same experiments, you showed agreement between theory and experiments from the spectral analysis to Fourier analysis. You were showing a nice plot of KZ versus KX or KZ versus E. So the theory there, was that inviscid theory or viscous theory?
Viscous.
Okay. Yeah, that makes sense. And then the third question was, I mean, you talked about this being you talked at some point about there being a super rotating SRI. So is that somehow different to a normal SRI, or is it basically the same mechanism, or is it somehow a new instability?
I mean, I'm not sure what would be the standard SRI. So I mean, based on the mechanism point of view that I explained in the presentation about the 2 double wave over reflection, the instability in the super rotation regime or even in the centrifugal rotation regime, they are the same.
Okay, so it's another way to think about it might be if you did a linear stability analysis, they'd be smoothly connected to each other, sort of normal SRI and super rotating.
Yeah, exactly.
Yeah. Okay, great. Thank you.
So Chris, you have a question. So if anyone wants to raise their hand, please do that, and then I'll go through you all in order. Yeah. So Chris, I think you have a question.
Yeah. Okay. So can you hear me?
Yeah. Hello.
Hello. Yeah. Okay. I got a question about your experiment. Yes. Your experiment had a radius ratio about 0.9, wasn't it? Yeah. Would it be possible to do one with a radius ratio much smaller? That is to say 0.1 or 0.2? Yeah.
I mean, yes.
Yes. Because I mean, if you do that, it's possible then you could see radiative instability as well as the standard SRI instability, because when you've got more room for the waves to come out, you have the possibility then of actually having a radiative instability in Taylor-Couette. And I mean, that would be quite fun, because then you've got the 2 different kinds of modes coming in at the same sort of critical Reynolds number. And so
I absolutely agree with you. And I guess it will be more fun. It will be more fun. I really agree with you. And in my case, the thing, I guess the lowest eta, the radius ratio, was not my experiment, but the people in Marseille in France, they had the setup about, I guess it was about 0.5. So that maybe they observed something more interesting than me. I mean, my setup was too short. so that if I have like 0.2, it means that I need
Yeah.
to have large cells. I mean, in this
Yeah.
case, the reason why I chose 0.9 was that I have like at least 10 vortices, so that I neglect the boundary effect.
Yeah.
So,
So
it means that I need to have a very tall.
you need to have a tall thing.
Mhm.
Yeah.
I mean, it would be really curious. I wanna see. It would be really nice, but I guess
Yeah,
so far
but
it
it
was,
hasn't really been done. I mean, I think the Marseille experiment, as I recall, didn't even really have the outer wall was a square rather than a cylinder, I think. I mean, it was just essentially a rotating axis, and they just weren't really caring about what happened at the other boundary. But that can be important, of course. Yeah. Oh, the other question I had about the experiment was the Froude. What was the Froude number in your experiment? I mean, you quoted the radians per second, but that didn't really mean it.
I mean, so the thing was that so I always kept the dimensional Brother-Weisler frequency equal to 3.18.
Yeah.
And
Okay.
The which is the
non-rotation
non-dimensional one was about it was quite low. I mean, the highest Froude number was like 0.1. So in the parameter space, I can really say that every Froude number is below 0.1. I can say that, yeah.
Quite small then, yes, right. Yeah. Okay, yeah. Right. Okay, thank you.
You're welcome.
David, you have a question?
Yeah. That's good. That slide that is there right now, the Taylor-Coët flowing stratified fluids. The boundary looks very similar to the boundary for Taylor-Coët flowing non-stratified fluids. Yes. So when you split it into 3 bits, so you've got centrifugal, mixed, and SRI. So is the Taylor-Coët, the normal Taylor-Coët instability still, if you did a stability analysis, is that mode still there, but these SRI and mixed have got a greater growth rate, or has one turned into the other?
I mean, I cannot really directly compare with the unstratified Taylor-Coët flow, where there are so many different flow regimes, but in my case, maybe if I look at really each point and then maybe I may find a difference, but the overall impression when I did my experiment, it was the SRI pattern keep sustained, and then maybe starting in this transition regime, they start to have some different flow pattern, but not very different, and then it become turbulent in the end. So that I was really not. I mean, it was quite difficult to identify exactly. I mean, maybe this LED turbulence is generated, so it was not really easy to figure out. I mean, let me say it was not, but at least I waited for some time to make sure that my observation, which was video recorded for some cases, they reached the saturation state, so they don't grow in time. And then I did keep keeping the inner cylinder Reynolds number for quite some time, and then increase the this parameter a little bit. But And one thing difficult was that this is now stratified fluid. So if you go up, then turbulence make all the mixing, so that the stratification profile after the experiment is no longer linear. So that like if I did the experiment and come back to this Reynolds number, it shouldn't be the same result, because the stratification density profile is changed, and because they're all mixed. So that that's why I did only this direction and stop the experiment here, and then wash all the experiment and then do another experiment. So that's how I did. So
okay,
I don't know if my answer was correct to your.
Just out of interest, how different is the shape of the stability boundary is very similar to the one that the classic one that you see for unstratified fluids. How does it look?
But,
how does it
but
compare
one thing
quantitatively?
different, you could, if you say about the stability curve itself,
Let's say,
I will
yeah.
say it is different compared to unstratified case, because this red curve corresponds to the centrifugal instability. So if we didn't have the stratification, this red line goes like this.
Okay.
But now we have the stratified-rotation instability, which is not governed by this criteria. So if I draw the line more for higher outer Reynolds cylinder, then this one, it looks like it. So you see that centrifugal instability never meet this dashed line, but you see that the SRI stability curve line meet this dashed line. So linear stability wise, it is different from unstratified case.
Okay.
Yeah.
Can I ask you another question about your second problem?
Sure.
Do you have a physical argument as to why things are more unstable once you become non-traditional?
That was more difficult. I mean, mathematically it was easier, but I will say physically no, it was quite difficult to answer. I mean, mathematically, I found the correct expression that the growth rate can be increased as I include some more term. I mean, mathematically it was quite clear, but physically it was a little bit difficult to explain. I mean, one thing I might guess is that when I consider the mean flow, which is in equilibrium, I consider the thermal wind balance, so that in the well, I'm not sure. It's just a speculation. It's not the correct argument, so I don't really know. When we do the stability analysis, we need to consider the steady state, and that usually we need, if we consider both rotation, then we need some thermal wind balance equation that give this term in the temperature equation. So I guess this term, I can still say no. I don't really know physically.
That's okay. All right. Thanks.
Any other questions for Junho?
I could just make a historical comment, maybe.
Yep.
It's more for comment than a question. I mean, in atmospheric dynamics, the inertial instability is most famous in its equatorial mode. So there were classic papers by Dunkerton in the early 80s. So he discussed in his 1982 paper, which was a double diffusive inertial instability paper, he discussed this notion of thermal diffusion destabilizing inertial instability. So he had some discussion of a Prandtl number 0 case. So there was no viscous diffusion, but there was thermal diffusion, and talked about destabilization. He also talked in that paper about how Newtonian cooling can also destabilize in the same way. So Newtonian cooling can damp out the buoyancy perturbations, and that promotes the inertial instability. So that's just a historical comment.
So I think in astrophysics, that instability in this context would be referred to as the Goldreich-Schubert-Fricke instability that was discovered in the 1960s. So that's often used often thought about in terms of radial shear, but also it can be thought of in terms of variation in the angular velocity along the rotation axis. And in the inviscid limit, you get an instability if the angular velocity depends on the rotation axis, which I think in your model corresponds with F being greater than 0 and F tilde being non-zero. Is that right? So you've got horizontal shear and not a radial shear. So I think that means that your horizontal shear, when you're not at the poles, then there's a component that's along the rotation axis. So in that case, I think that in the inviscid limit would correspond with this so-called GSF instability. And I think that instability has been looked at since the 60s, but not much work has been done on that.
I mean, I somehow agree. Yeah, I mean, I've been studying this GSF instability recently, and yes, probably it's relevant. Yeah.
But yeah, just thought I'd point that out. But yeah, it's a nice talk. So I did actually have one other question about the earlier part of the talk, about that figure that we're all talking about, the one with the SRI and the centrifugal instability on it. Mine was quite a very quick question about that. The one with the different regimes that you had a bit below when you had the experimental results that Chris, Stephen and David are all asking about. So the question I asked is just how you, I want to ask is how you determine the what the symbol is. Is it just by eye? So whether it's turbulent or transitional, is it just by eye, looking at how
by eye.
Okay, thanks.
I mean, I didn't have any other tools.
Yeah,
I really had my own eyes, that's all.
That makes sense. Thanks. So any other final question for Junho? If not, let's thank Junho again.
Thank you. Thank you for listening.
Thank you.